The method in the previous videos clearly preferable to trigonometric substitution. However, in order to use it, we need to know how to decompose that fraction 1 over x squared minus 5x plus 6 into the partial fractions 1 over x minus 3 and negative 1 over x minus 2. So the denominators depend on how we factor x squared minus 5x plus 6, but there are also the coefficients in the numerator. So for the first fraction, the coefficient is 1 over x minus 3. And for the second fraction, the coefficient is negative 1. So we need to figure out how we can find those coefficients. But first, we need to talk a little bit more about factoring. And we know from algebra that every polynomial with real coefficients can be factored into linear and irreducible quadratic factors. And in order to show what I mean by that, let's do an example that has all of these ingredients. So in this example, we are asked to factor x to the power 5 plus x to the power 4 minus x minus 1 using factoring by grouping. So we divide up this expression into two groups of two terms. We're combining the x to the power 5 and the x to the power 4 in the first group. And the second group is our negative x minus 1. So in the first group, we see that these two terms have a common factor of x to the power 4. And then the second, and if we factor out that x to the power 4, we're left with x plus 1. In the second group, we can factor out a factor of negative 1. And then we're left with x plus 1 as well in the second group. So what this allows us to do is to factor out the x plus 1 in both of these terms. So if we factor out an x plus 1 for the first term, what we're left with is x to the power 4. So we have x plus 1, and then times for the first term, we're left with the x to the power 4. And if we remove the x plus 1 from the second group, we're left with minus 1. So we've set our first step into completely factoring this expression. So we now have that the expression is x plus 1 times x to the power 4 minus 1. But we can go even further than this. So what we have to do is we have to recognize that second factor, x to the power 4 minus 1, as the difference of two squares. So we can write x to the power 4 minus 1 as x squared minus 1 times x squared plus 1. And I'll just remind you of that difference of two squares. If you have a squared minus b squared, and you have to factor that, you can factor it as a minus b times a plus b. And you can verify this fact by just FOILing out the right-hand side of this expression. So for us, x to the power 4 minus 1 can be written as x squared squared minus 1 squared. So our a is played by x squared and the b is played by 1. So that's why we have x squared minus 1 times x squared plus 1. And then what we see is that we can do the same thing for the middle factor. So the x squared minus 1 is again a difference of two squares. And now our a is x and our b is 1. So we can factor that x squared minus 1 is x minus 1 times x plus 1. Now the last factor, x squared plus 1, is a so-called irreducible quadratic factor. This factor can not be factored any further because if you think about the solution to x squared plus 1, that would lead to x being equal to plus or minus I. So that tells you that if you have to involve imaginary numbers or complex numbers, you cannot factor any further. So in general, if you have the expression ax squared plus bx plus c, then it is an irreducible factor if b squared minus 4ac is less than 0. And you might recognize that expression as the discriminant of the quadratic equation when you set it equal to 0. And so when the discriminant, which is the part that's under the square root in the quadratic formula, is less than 0, then complex numbers are involved. And when we talk about factoring, we talk about factoring over the real numbers. So we don't want to introduce any complex factors. So at this point, all that we have to do is kind of clean this up a little bit and combine that x plus 1, those x plus 1 factors. So we can write x minus 1 times x plus 1 squared times x squared plus 1. And that is the complete factorization of that expression. So we're going to use that factorization to rewrite a fraction where the numerator is a polynomial p of x. And how we need to, or how you do that, is what we're going to talk about next. So this process is called the partial fraction decomposition. And the first thing we have to check is that when we have a fraction, we need to look at the degree of the numerator and the degree of the denominator. So if the part that's on top has a degree that's greater than or equal to the degree of the denominator, we have to perform a long division, and that will split our fraction up into a polynomial and then a part where the numerator has a degree that's strictly less than the degree of the denominator. So in our example, with the p of x over x to the power 5 plus x to the power 4 minus x minus 1, that polynomial has to have a degree of 4 or less. Then the next step is to factor the denominator. And when you factor the denominator, you'll end up with factors of the form px plus q to a power. So in this previous example, we have 2 of those examples. And then also we have some irreducible quadratic factors, and we have an example of that too. Then for linear factors, each factor of the form px plus q to the power m, the partial fraction decomposition must include a sum of m fractions. So we start out with a constant a1 over that linear factor, and then another constant a2 over that linear factor squared. And then we do that as many times as needed until we reach a coefficient a sub m and then the linear factor to the power m, which depends on how many times that factor shows up in the factorization. So for quadratic factors, then each irreducible factor of the form ax squared plus bx plus c to power n leads to a sum of n fractions, and each fraction has a linear numerator. So it's a constant b1 times x plus a constant c1, and then your quadratic term on the bottom. And then again, you repeat that as many times as necessary, depending on how often that factor appears in the factorization. So in our example above, we only need one term, but conceivably if the quadratic factor has a factor or a power of n, we have to have n of these terms.